a tree, or represented by the letter T, yeah, is a simple graph. It is a graph such that for every pair of vertices V and W, yeah, there is a unique path from V to W. This is the key characteristic of a tree, which you cannot have in graph. Graph, you may have more than one path from V to W. Just now, if you have seen an example of a graph, right? If you have been looking at it carefully, there are some parallel edges, right? Parallel edges means that between two vertex, when you have parallel edges, that means there are more than one path to get from the first vertex to the next vertex. But for a tree, no, there is no parallel edge. There's only one path from every vertex to every vertex. So that is what a tree is. Now, a more specific tree is called a rooted tree. Okay, a rooted tree. It is a tree where one of its vertices is given, is assigned as a root. Root is always at the top of the tree. Yeah. So tree in data structure is not like the biological tree. It's an inverted tree where the root is at the top level, whereas the leaves is at the bottommost level. In between, all these are branches. Okay, all these are branches. Now, in the graph terminology, it would have been root vertex, edges, branch vertex, or branch vertices, leaf vertex at the end. Yeah. So let us analyze the three diagrams below. Number one is a graph, but not a tree. Now, how do we know? You look at this. From V to W, there are two ways to get, there are two paths to get from V to W. The linear path, very straightforward, or you can use the zigzag path. So this is not unique, right? So it's not a tree. Now, the second diagram, the second drawing is a tree because to get from V to W, there's only one path. Likewise, for every other vertices, also the same. It is impossible to have more than one path. Yeah. But this is not a rooted tree. It's just a general tree or a free tree. A more useful tree is called rooted tree, whereby it looks more organized. We have multiple levels. From level 0, which is the root, it branches out, yeah, until at the end we will have the leaves. Now, how many levels can there be? There's no limit. It can be a very tall tree, and not necessarily, the branching will be equal. Sometimes it branches 3, sometimes it branches out 2. There's no limit to that. Yeah. Some terminology. Vertex. Yeah, all these are vertex. They are also called node. In tree terminology, they're also called node. We have a branch node. You see level 1, all these are branch nodes or branch vertices. And then the last level, all these are leaf nodes. Imagine this like an inverted tree. Yeah. Or because leaves grow at the tip of the branches. Huh? So these are called leaf nodes. Other terminology will be sibling node, parent node, and child node. Now, look at this. Root, underneath root, right, there are 3 child nodes. 3 child nodes. So these 3 child nodes at level 1, the parent is the root node. They share the same parent, which is the root node. Now, this child node of root is the parent of nodes at level 3. So it is relative. It is relative. You see, at level 1, the nodes here is the child of root, but they are also the parent of nodes in level 3. So parent node, children node. Now at level 1, you see these 3 nodes are of the same level, right? They share the same parent. So these are called sibling nodes. sibling nodes. You know, they're brothers and sisters. Yeah. So some terminology which are useful when we want to refer to the nodes in a tree. Okay. So I have explained this just now. Yeah. So these terms are relational. Like here, if you look at my mouse pointer, the level 1, level 0 is the root node, level 1 is the branch node, right? On the one on the left, you see, this is a child to the root node, but it is also a parent node to the nodes at level 2. Yeah, level 0, level 1, level 2. And then nodes at level 2, because they all share the same parent, they are sibling nodes. How about level 1? Level 0, level 1. So the one on the left and the node on the right, these are sibling nodes because they share the same parent. No matter how you draw it, right? Here, because we draw it very nicely, but if I don't draw it nicely, like maybe the node on the right hand side is drawn higher than the one on the left, doesn't matter. As long as they share the same parent, they are called sibling node. Okay, some terminology. We are not using it for any application yet so far. Some three characters. Let's look at one theorem. If T is a graph with n vertices, the following are equivalent. T is a tree. T is connected and acyclic, having no cycles. This is a very important criteria. Only a graph can have cycles, yeah, but graph that doesn't have cycle, they are known as trees. And T, we have n minus 1 edges. All right, whereby n refers to the number of vertices. Now, let's look at how we assign levels of the nodes in a tree. Let T be a rooted tree. Now, from this slide onwards, we are not talking about free tree or general tree. We are talking about rooted tree, which is more useful in most computing applications. Yeah, rooted tree. So rooted tree is very easily recognizable because there's only one single node at level 0. And then the rest are its children and grandchildren. Yeah, children and grandchildren nodes. The level V of vertex V is the length of the simple path from V to the root of the tree. Okay, so you see, like this one, level 1. This is level 1. We count it from the root. Root is considered level 0. So here is level 1 from the root, level 2 from the root, level 3. Okay, I think there's another. Okay, level 3 from the root. Now, how about this one? You see my mouse pointer? I'm not sure whether you can see it clearly. I'm shaking it so that you can see the mouse pointer. All right, you see my mouse pointer? So this node, right, belongs to level 2. Yeah? This one, this one, this one, this one, this one, they all belong to the same level. Now, if we redraw this, it should look like this. If you redraw them. So what is the height of this tree? We count the furthest level as the height of the tree. In this case, it's level 3. So the height of this tree is 3. The height of a rooted tree, T, is the maximum of all level numbers of its vertices, whereby we find the max level of the vertices. And it's the last vertex, and this vertex is an element of all the vertices of that particular tree. That's how we read this. Let's look at one example of rooted tree and levels. Let's use a more familiar tree. Let's look at this one in an organization. Yeah, we may have the CEO or the president, and then reporting to the vice president, vice presidents, we have two vice presidents here. One is vice president for academic, the other one is vice president for administration. Under vice president for academics, we have 4 deans: deans of business, deans of A&S, dean of natural sciences. Yeah, and likewise for VP, we have director of maintenance, business officers, payroll, human resources. The branch on the top is longer, you see, because under dean business we have a chairs for different departments. Yeah, chair for accounting department, chair for finance department, marketing department, so on and so forth. Yeah. Oh, yeah. The admin also has one additional branch here. You see, under director of maintenance, facilities department, electricity department, and waste management department. So how many levels are here? How many levels are here? The key is to find the root. The root is level 0. So what is the height of this tree?
3.
Okay, let's find out. So root is 0, 1, 2, 3. Correct. So this tree is drawn horizontally. We need to find where the root is. It is a rooted tree. Then only we can determine the branches. We can determine the levels by aligning them nicely. Another example of application of rooted tree is in Huffman Coding. Okay, as we go through the slides for Huffman Coding, you will realize the significance of Huffman Coding for encryption. So let's look at this diagram. Apparently, this diagram is a tree, right? At the bottom of the tree are leaves. So these leaves will contain characters. Yeah, characters. Characters can be alphabet, can be number. Coding is used for encrypting text. Yeah, for encrypting text, and text can be alphabetical, numerical, and symbols. These symbols are not limited to computer keyboard symbols or mathematical symbols. It may also include symbols from languages such as Chinese, Japanese, Korean, Arabic, Urdu, so on and so forth. Yeah, but we will limit ourselves to the standard characters that we have on keyboard, which are alphabets, numbers, English alphabets, numbers, and standard keyboard characters. So let's say this is what we call a Huffman tree, and the use of Huffman tree is to encode words. Now let's try one word. Let's have the word bad, B-A-D, bad. Yeah, B-A-D, bad. So for the word bad, what is the code for the word bad? Now this is how we go about. Yeah, the letter B, we can replace it with, start reading from the root, 1, 0. So we put 1, 0 for letter B. How about letter A? What is the code for letter A?
1, 1.
Correct. 1, 1. How about letter D?
0, 0.
0, 0. Okay, perfect. So let me write it down here. B is 1, 0. A is 1, 1. D is 0, 0. So the code for the word bad is 1, 0, 1, 1, 0, 0. Now, suppose that I give you, let's forget about this. I give you this code. What word does it represent? Of course, this does not ring a bell, right? It only rings a bell. It's only meaningful if I say this code is used together with this Huffman tree. Then only you'll be able to decode. You'll be able to decode. Yeah. So you will look at this. Okay, 1, 0. 1, 0 is B. So okay, this is B. 1, 1. 1, 1. Okay, it's A. And then 0, 0. See, you decode it back to the word bad. Okay. Now let me ask you another question. Try to decode this symbol. Try to decode these binaries. Yeah. Okay. Let us try to work this out together. Decode 0, 1, 1, 1, 1, 0. What could be the answer? So you can only decode if you are provided with a Huffman tree. No Huffman tree, there's no way to decode it. So we are using this Huffman tree. So what's the answer? Anybody?
CAB.
Yes, CAB for the word cab or taxi. Yeah. Now, apparently, this is a very small Huffman tree. To make it more useful, we could have a very, very big tree that covers all the alphabet, numerics, and symbols on the keyboard. Then you can use this bigger Huffman tree to encode and decode any text. Yeah. But we are using a small Huffman tree here to help everybody to understand how the tree is used for encoding and decoding. Now, let us look back at the tree. Okay, let us look back at the tree. Now, you see this tree, right? This tree is a binary tree because you have left, right at every level, you know, left, right. The one on the left-hand side, you assign with value 1. The one on the right-hand side is assigned with value 0. So this is not only a rooted tree, but it's also a binary tree, rooted binary tree, because every level, the node has 2 branches only. 1, 0, 1, 0, 1, 0. The one on the left-hand side is always 1. The one on the right-hand side is always 0. Yeah, that's how Huffman tree is constructed. Now, when do we use this? Now, we use Huffman code as an alternative to ASCII code. Yeah. Apart from ASCII code, right? We also have UTF-16. But I'm not going to talk about UTF-16 here. That belongs to another course. I will just compare ASCII code versus Huffman code. Yeah, the pros and cons of each. Now let's look at the other slide to help us understand what I mean by ASCII code. Does anybody know the full name of acronym ASCII? Anybody can help me? What is ASCII? Anybody wants to try? Nowadays, information is easily at fingertip.
American Standard Code for Information Interchange.
Okay, good. Thank you for trying out. Yeah? I can't see the name of the person who actually answered this when I'm in this mode, but thank you. Yes, correct. ASCII stands for American Standard Code for Information Interchange. But what is it actually? Now, all these characters, all these characters, right? They are found on your keyboard. Our keyboard, our standard keyboard is based on ASCII. Whatever symbol here is found on your keyboard, on your laptop, on your workstation, maybe your smartphone virtual keyboard. It's a standard keyboard design for the physical keyboards as well as the virtual ones. You can try to find out on your keyboard whether you can produce all these symbols or not. Not all of them are symbols. Some of them are controls. For example, this is for your delete button on your keyboard. Yeah, DEL. And of course, I'm not able to tell, some of these control buttons. Yeah, I don't have the. I mean, I can search for it, but that's not important for now. Yeah, the thing that I would like to point out to you is that let's try this. Let's try to find out the representation of ASCII code for the letter alphabet A. So where's alphabet A in this ASCII table? Now this table is quite standard. You can Google image for it. Yeah. Okay, so let's look at it. Letter alphabet A. Be careful because there's also lowercase a. We are looking at the uppercase alphabet A. Okay, so according to this table provided by ASCII, yeah, the symbol for A is 100, binary 100, 0001, 0001. Correct? Okay, how about, okay, I'm going to skip B and C. Just jump to uppercase D. Let's look at uppercase D. So where's uppercase D? Okay, again, it's a 100, binary 100. And then on the left hand side is 100 up to here. And then on the left hand side is 0100. Okay, so this table will actually give you the binary of all the characters. Yeah, of all the characters. Binary of all the characters. In fact, whenever you press your keyboard, when you press the letter uppercase A on your keyboard, the electrical signal will produce the binary code. And it's a standard. It's a standard. Every keyboard will produce the same code. Yeah. So the advantage of ASCII is that it's standard. Always the same. Everywhere. Always the same. But there is one disadvantage. You see here? A, B, C, D. They are made up of how many bits? 1, 2, 3, 4, 5, 6, 7. Actually, it's 8 bits. No? 1, 2, 3, 4, 5, 6, 7. It's actually 8 bits. Yeah. So 1 byte, 1 character. So ABCD already taking 4 bytes. Yeah, because 8 bits, right, is 1 byte. So here ABCD, 1 byte, 1 byte, 1 byte, 1 byte is already 4 bytes. So if we send this through the network, if we encrypt this and encode this and send it through the network, we need to reserve 4 bytes on the network just for 4 letters. Such a waste, right? 4 letters, 4 bytes. Now, let's look at a more intelligent idea introduced by this guy called Huffman. He said that sometimes we can skip ASCII. We can create our own code. Let's create our own code. Now, when we create our own code, the binary is much shorter. You see, for letter A, only 2 bits. B, 2 bits. C, 2 bits. D, 2 bits. As compared to ASCII. ASCII, 8 bits, 1 byte. So you see, Here in total, 1, 2, 3, 4, 5, 6, 7, 8. So all this is only 1 byte. You want to send ABCD over the network, it's 1 byte. But if you use ASCII to send ABCD over the network, it's taking 4 bytes, 4 times longer. Imagine this. This is just ABCD. What if you are sending a long text or maybe videos over the network? It'd be humongous, right? So the idea of Huffman is to generate shorter representation of the characters that we want to send over the network. That is the purpose. Got it? Whereby the size is many, many times smaller. But then the question is, why do everybody stop using ASCII and just use only Huffman? Why don't we just use only Huffman? Stop using ASCII. Forget about ASCII. Why not? Why we are still keeping ASCII? The reason is because ASCII, we are still using it for keyboard. Because keyboard, you're not sending it over the network. So no big deal. 1 byte, 1 byte, 2 byte, 2 bytes, no big deal. Yeah, we are using our computer RAM. But when we send it over the network, then only we have to pre-process to generate the Huffman tree in order to encode. So there's some processes involved, you know. You can save size, but you spend more time on processing. Whereas if you use ASCII, immediately you just refer to this table, you get the code. No need to process. But if you use Huffman, first you have to analyze all the letters, generate the Huffman tree, generate the Huffman code table. Then only you send. And then the other side must receive the Huffman tree, and then they use the Huffman tree to decode. One side to encode, the sender encode, the receiver decode. And every time you have to generate different Huffman tree. ASCII, standard. Huffman, not standard. Huffman, let's say I want to send one WhatsApp message to you. Yeah, my student. I want to send one WhatsApp message to you. When I send the first message, it will generate its own Huffman tree. When I send the second message, it will generate another Huffman tree just for that message. So there's some processes involved on the application. So you see, in computing, if you want to save memory, you have to spend more on the processing. If you want to save processing speed, then you have to spend more on the memory. It's always something. There's always cost for something. So you need to decide whether processing speed is more important or space is more important. Yeah. Okay, let us learn how to produce a Huffman tree. So what is a Huffman tree? Obviously, it's a tree. It's a rooted tree. It's a binary rooted tree. Yeah. It's a prefix tree, variable length encoding where characters with a higher frequency are represented by fewer bits. Okay, this is the interesting part. Characters with a higher frequency are represented by fewer bits. So that means, you see, when you send a text, some alphabet, some letters are more frequent, right? For example, A is very, very frequent in most text messages. A is very frequent, correct or not? Maybe character like Q or Z is not so frequent, correct or not? So Huffman coding is exploiting these differences to produce a Huffman tree. If the character is very frequent, we should have a smaller code, shorter code. If the letter or the character is not so frequent, okay, we can afford to have a longer code for it. That way, the total message, we have shorter code. The total message will have shorter code. Now, how is this useful? Now, this is useful when we compare with ASCII. Now, suppose that I want to send this string across the network. So how many characters are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 characters. Do you remember in programming, usually character is what size? Char is what size? Integer is 2 bytes, but there are also 4 bytes integer. Integer is usually 2 bytes. Double is 4 bytes. Cha? Cha is 1 byte, right? If you recall in programming, correct or not? So just now, how many characters we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have 15 characters. So if we use ASCII, we have to allocate 15 bytes. We have to allocate 15 bytes if we use ASCII. But let's not use ASCII. Let us use Huffman coding. With Huffman coding, we can have less bytes. We can have more saving of space. So let's find out what is the number of bits if we use Huffman coding, shall we? Okay, so before we can do that, we need the tree. We need the Huffman tree, right? Just now, when I show you another example, I already provide you with a tree. So you can use the tree to encode and decode. But in our problem now, the tree is not even there. So what should we do? These are the steps. These are the algorithm to produce the Huffman tree. First, you need the initial string. Okay, you need the initial string. Produce from the initial string, determine frequency. Then from the frequency, come up with a priority queue. Sort the priority queue from less frequent to more frequent. And then for each character, one by one, in the queue, create a tree, create a new node, and then decide the left node and the right node. And then you sum up the left node and right node to come up for the value of the new node. And then you insert the new node into the tree and also update the new node frequency into the queue, into the priority queue, and resort again. And keep doing this until all the characters in the priority queue is done. Easy, right? Okay, not easier. If you just read like this, it won't make sense to you. Let us do it together, okay? So you look at this, what do you call this? Initial string. Remember, this is called initial string. Now, remember, memorize this. B, C, A, D, 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 C, C, A, C, A, C, A, C. Because I need you to produce the priority queue after this. Just kidding. No need. I just copy paste. No need to memorize. Yeah. So this is the same initial string. Yeah, I was just kidding. No need to memorize the initial string. This is the same initial string. I copy paste from the previous page. Now, the first thing you need to do, according to the steps just now, for each character, okay, so what characters we have here? B, C, A. Okay, another A we skip because we want the unique one only. D. Okay, D, D, C, C, A, C, C. Okay, all are repeating. Okay, so we have B, D, B, C, A, D. So what do we do? We count how many B? 1. Okay, there's only one B. How about C? 1, 2, 3, 4, 5, 6. Correct or not? 6. Yeah. And then A. How many A? Count for me. Please follow.
5.
Okay, good. I mean, you can just read from here 5, but I do hope that you actually try to count. Yeah. Participate. Because when you participate, you will learn. And then D, of course. 1, 2, 3. Okay,
3.
all covered already, right? Nothing left out. Now, so now you have the frequency. You have the frequency of every character in the initial string. All right. And then sort them from lowest frequency to the highest frequency. Now it's 1, 6, 5, 3, right? So when we after sorting, it'll be 1, 3, 5, 6. 1, 3, 5, 6. After sorting, B is less popular. The most popular one is C. Yeah, most popular is C. B is least popular. Now, after we sort, this is called the priority queue. This is the priority queue. Remember that. This priority queue is very important for us to construct our Huffman tree. You can forget about the rest already. At this point of time, forget about the rest. If you do the steps correctly, you just need this priority queue to produce the tree. Okay? Okay, follow me, follow me. Now, from this 1, 3, 5, 6, which one has the smallest? B and D, This one has the smallest value, right? So what you do is, you put the smallest one on the left-hand side, B, with the value 1, and then the second smallest, D, on the right-hand side, 1 and 3. Now, create new node. This is what we call new node. N-E-W. Okay, new node. So, new node, what do you do here? You take 1 plus 3, you get 4, right? So this is a new node. Now, what happened to the priority queue? Just now, you have B and D, right? You have taken them out, isn't it? You put it here already, isn't it? So we are only left with 5 and 6. 5 and 6. But wait, we must update the queue node. We must update the queue, the priority queue with the new node. The new node value is 4, right? So apparently we're going to put it here lah, because 4, 5, 6, right? From small to big. Now, look at the step just now. Insert new node into the tree. Update new node into the queue and resort. Resort. This is what we are doing here, right? Resort. So 4, 5, 6 is correct, huh? Okay. Now, forget about this already. We just look at this new queue node, 4, 5, 6, and the existing node here. Now, what do we do here? Now, let's look at here. We have 4, 5 as the smallest pair, right? We have 4, 5 as the smallest pair. So we are going to put 5. You see, 4 is already here, isn't it? 4 is already here, isn't it? Yeah. So 4 and 5. So 5 we put to the left or to the right?
Right.
Why do we put to the right? The bigger one is always to the right. That is the rule. The bigger one is always to the right. The smaller one is always to the left. You see, look at this. You see, left, small, right, big. Left, small, right, big. So at this point of time, when I have 4 and 5, I need to place 4 already here. Okay. So 5, do I put to its left or to its right? So apparently to the right lah, right or not? Because it's bigger. So now we have 4 and 5. What do we do now? We create a new node. A new node. We take 4 plus 5, 9. This is a new node. And then we must update the queue. We must update the priority queue. You forget about this one already. Update the priority queue. Just now we've taken 4 and 5 out already, right? So we are only left with 6. So the 9 here is bigger than 6 here, right? So we put on the right hand side, not the left hand side. So now we are left with C with frequency 6 and new node with frequency 9. Now, with this, we are going to add. Okay, we don't have choice because we only have C, right? Left. So this C we put to the left or to the right of 9. Apparently to the left of 9, right? This 9 should be on the right hand side because it's bigger. So 6 should be on the left, not on the right. Correct or not? So C is on the left. 9, the new node is on the right hand side. 6 plus 9, 15. So another new node, and we use this another new node to update the queue. Now inside the queue, is there any more character? No more character already, yeah? You see, all the character no more already. So we are only left with a new node. So that means new node here is the root. This new node is the root. No more already, right? So at this point of time, the next thing that you do is we label the left and right edges with 0, 1, 0, 1, 0, 1. Okay? We label them. Yeah? So now this is what we call our Huffman tree. Yeah, this become our Huffman tree. So just now, we have graphically analyzed how this is done. These are the steps. And this is the graphic, the illustration of how these steps are done. Yeah. Now you may ask here, hey, how come in this example it's not 0, 1? It's 10, 10, 10, 10. The answer to this, right? Okay, if you use 10, then all the children must be 10. You cannot have 1001. That is the answer. Okay, because as long as when you send this tree to the other side of the network, the other side of the network will refer to the same tree. So if you want to put 01, make sure everybody is using 01. If you want to put 1 on the left, 0 on the right, make sure everybody is doing the same. Okay, like this one, see? Yeah, we're not using 10, but we're using 01. 01, 01, 01. You won't find 01, 10, 10. No, you won't mix up. All right. Let's look at another example. Okay, let's look at another example. Now, given priority queue, okay, this one we already skipped many steps lah. Instead of using the initial string, I straight away give you the priority queue, whereby the characters frequency has been sorted from smallest to biggest. That's why it's called a priority queue. If it's not sorted, it's not called a priority queue yet. Yeah, it must be sorted. So to produce Huffman tree, you need the priority queue, but the priority queue is needed to start the bottom, from the bottom, and then you work all the way up. So every time you're going to update the priority queue. So let us look at this. I don't think I want to explain this time. I would rather have you try to analyze this on your own. Okay. Let's have maybe 5 minutes for yourself to analyze this. Okay, I'm going to be silent and try to work out on your own first. Yeah, 5 minutes. Okay, are you able to follow? I hope you are able to. If not, you watch this video, you watch the previous video again. Just now I already done some illustration without voice, and hopefully you got it. Okay, so we can do this for different kind of initial string. Yeah, we can do this for different kind of initial string. Every group of characters will generate its own Huffman tree that you use for decoding. And then on the other side, after send the text over the network in the form of binaries, because when you transmit anything through the network, it'll be in binary form, right? Not characters. So you have shorter code compared to ASCII. ASCII is definitely 1 byte per character. But if you use Huffman, it's much shorter than 1 byte. Yeah. Let's look at example 3. Now, this is a different Huffman tree than just now. And let's analyze how these characters are arranged. This one I didn't give you the priority queue, but I hope by just looking at the character and its frequency, you will understand why on the left, why on the right, and then where does this number 4 come from, and why letter A with frequency 5 is placed on the right hand side, not on the left hand side, and then where does this number 9 come from, and then the letter C, why is it placed on the left hand side of 9, not on the right hand side of 9, and how we get 15. And in this case, we only have A, B, C, D. So A, B, C, D already covered. No more alphabet, so we are done. So this is the Huffman tree. Why is it drawn this way, not the other way? Then usually we put 0, 1, 0, 1, 0, 1. Of course, you can also put 1, 0, but I would prefer that you put 0, 1 in your answers, because it's more standardized, yeah, when it comes to me for marking. Now let me ask you, in case of sim frequency, let's say here is easy to decide. Okay, let's look at this one, 4 and 5. If 4 and 5, of course 5 must be on the right hand side, right? But if you compare 6 and 9, of course 6 is on the left hand side. Smaller one should be on the left hand side. But what if similar? Let's say C, example, imagine instead of 6, let's say C is also 9. So if C is also 9, do we put on the left hand side or do we put on the right hand side? The answer is, when the frequency is similar, either side we do. You can put left or right. It will still produce an optimal Huffman code. That's the answer. Yeah. But for myself, I usually put on the left hand side. All right. But you can put on the right hand side, no problem. If it's equal. Cool. Okay. So that's for example 3. Now, let us learn how, again, okay, actually I have explained this earlier. This is more of reinforcement. Let us learn how to encode words using a Huffman tree. Now, you are given the following Huffman tree with a set of characters A, B, C, D, and the Huffman tree is as such. It's already given to you, okay? And you don't have to worry about the priority queue. You don't have to worry about initial string. You don't have to worry about the frequency, because the Huffman tree is already there. The only time you have to worry, where's the frequency? Where's the priority queue? Is if you want to produce the Huffman tree. If Huffman tree is there, what you need to do? You use it for encoding or decoding. Got it? Now, how do we encode CAB? One example is already given here, right? So CAB is very easy. C is 0, 1. A is 1, 1. B is 1, 0. That's it. How many bits here? 1, 2, 3, 4, 5, 6. 6 bits. Suppose I use ASCII encoding. It will be 8 bits, 8 bits, 8 bits. So altogether it will be 24 bits. Or equivalent to 3 bytes. But if using Huffman, how many bits? 1, 2, 3, 4. Only 6 bits. Less than 1 byte. You see how small it can become, right? Okay, let's try it back. BAD. What would be the Huffman encoding? Okay, you can put your answer in the chat. What is the encoding of BAD using Huffman? Okay, Muhammad Iqbal share his answer of 101110. Sorry, I repeat 101100. Okay, 1011 and 00. Okay, perfect. Correct. So only 6 bits, right? Very small. Now, suppose that we want to find the ASCII for BAD. Want to find the ASCII for BAD. What would it be? Okay, for this, I have to go back to the ASCII table. Or in fact, you can just Google ASCII code for B, ASCII code for A, and ASCII code for D. Maybe instead of me referring back to that, somebody can help me to find ASCII code for B, ASCII code for A, and ASCII code for D. So it'll be faster for me. Can anybody help me? Okay, somebody do B, somebody do A, somebody do D. You just Google ASCII, but make sure it's capital letter B, capital letter A, and capital letter D. You just Google for it. Actually, it will give to you. While waiting for that answer, I just quickly show you the ASCII code table just now. BAD. Let me see whether I can clear this or not. Find the options. Erase or ink on slide. Okay. So just now was B. Anyway, I already have it here, right? BAD, right? So BAD. B, okay, your friend already shared there. 1000010. Okay, correct. A is okay, somebody has found B. Okay, I wait for A. Maybe I just type A here in the meeting chat. A 0B 1 0 2 3 4 5. And then D will be 8 0 B 1. Okay, so I'm going to copy that here. So B is 0 oops 1. I wonder if I can enter text. Okay, I'm not sure how to enter text here. Then I just type. I just write 0 1 1 2 3 4 4 zeros. This is for the letter B, already taking 8 bit, and then for letter A, and then for letter D, you see? Like this is already 24 bits as compared to here only 6 bit. That's why people want to use Huffman encoding when we want to send something through the network. But of course, the drawback of Huffman coding as compared to ASCII is that we also have to send the whole tree together with the message to the other side of the receiver. Yeah. So I leave this other slide for you to try out on your own for a different Huffman tree for different sets of words. Like I say, the drawback of Huffman encoding is that we will have different Huffman tree for different messages. But if you're using ASCII, it is standard. Whatever message you want to send is always the same standard ASCII table. But Huffman, no. That is a drawback. Yeah, there's a price for every convenience. You see, like this one. Using this Huffman tree, the letter rate is encoded as this. But if I use a different Huffman tree, obviously the encoded binary will be different. That's why we have to send the same Huffman tree from the sender to the recipient so that the recipient can use this Huffman tree to decode. One side, the sender encode, the recipient decode. Makes sense, right? In network, sender encode, produce the tree, produce the encoded messages. Recipient receive the same Huffman tree. Recipient receive the encoded binary. They use the Huffman tree to decode it. So Huffman decoding is very simple, right? So like I said, like we have tried earlier, we just simply start from the root. Now, in this case, let's say you are the recipient. From the network, you receive the following binary, but you already know this binary should be decoded using this Huffman tree. So what could be the message after you decode it? So what is the answer for this?
Rate.
Rate, yeah? 00 for R, 00 for A, 000 for A, 011 for T, and 100 for E. So on the recipient side, over this other side of the network, they need the same Huffman tree. That means if you're the sender, you need to send the Huffman tree. Yeah. You know, just like later on when you learn network encryption, they have the key, right? And then the crypto and the encrypted messages. The crypto is used as the lock to decrypt the decoded message on the other side. The same idea here, but of course, that one is more complex because they use a more complex algorithm to scramble the arrangement. Now, this one is the purpose of this one is not so much on security, but to save space. Not so much on security, but to save space. Yeah, Huffman encoding, Huffman decoding is not good for security because people can crack it. But saving space, yes. Okay, when you are free, you can try to work out on this example. So the text that we are using here is HTTP, right? So what are the characters here? We have character less than, character uppercase H, character T, character P, character, oops. This one is a bug. Character greater than, character slash. Then you just count the frequency. Like less than 1, 2, okay, only 2, hash 1, 2, T, 1, 2, 3, 4, P, 1, 2, greater than 1, 2, slash only 1. Now this is not a priority queue yet because you haven't arranged. Priority queue is after you arrange, right? So from small to big. Oops. Then this is the priority queue, whereby the left-hand side is character, the right-hand side is the frequency. Guys, sorry, it's not so clear. Okay, and then from this priority queue, you can produce a Huffman tree, and you can use it to encode and decode HTTP. All right. So for question number 3, can we decode the binary without the same Huffman tree as reference? Yes or no?
No.
No, definitely no. If you use different tree, you won't get back the plain text. After you have encrypt it, to binary, you won't be able to reverse it. You need the same Huffman tree. Okay, so these are the main thing that I would like to highlight in this chapter. This thing aside, complexity is actually a side thing, not the main thing that I want to highlight, but it's just for me to point out that the complexity of Huffman coding is reasonable because it's only n log n. And if you remember time complexity from the earlier chapter, yeah, it is not that bad. Yeah, it's not exponential. Yeah, it is slightly more than linear. Yeah, it's slightly more than linear. The more characters you have, it will slow down, but it won't really freeze. Yeah, if you look at the n log n graph, yeah, you can always Google for it, or you can refer back to the earlier chapter to see the graph, how the time increases when you increase the number of characters. It will increase, it is more complex than linear. It's not linear, it's more complex than linear, but not so bad, not like exponent.